The ML inequality is a blunt but powerful safety net. It doesn't calculate an integral exactly, it just proves the integral can't be bigger than some ceiling value. Pattern to recognize: whenever an integral's exact value is hard to pin down directly, especially arcs that are shrinking to zero as a radius grows, reach for the ML inequality instead of trying to integrate directly. The idea is this: find the largest possible size the function could be anywhere on the curve, call this m. Multiply by the curve's total length, call this L. The integral size can never exceed m times L. Stated precisely, the magnitude of integral over c of f of z dz is less than or equal to m times L, where m is the maximum of the magnitude of f of z for z on c, and L is the length of the curve c. Now separately, Cauchy's theorem itself only works cleanly on a simply connected domain, meaning the region has no holes cut out of it. If there's a hole, like a missing point where the function isn't defined, the theorem needs modifying. Pattern to recognize: simply connected means any closed loop drawn inside the domain can be continuously shrunk down to a single point without ever leaving the domain. A domain with a hole fails this test, since a loop around the hole gets stuck. Definition: a domain D is simply connected if every closed loop inside D can be continuously shrunk to a point without leaving D. Cauchy's theorem, which requires a simply connected domain, says this: if F is analytic throughout a simply connected domain D, and C is any closed curve inside D, then the closed loop integral of f of z dz around C equals exactly 0. Now for the worked example, we want to show that the integral over c sub r of 1 over z squared dz approaches 0 as r approaches infinity, where c sub r is the upper semicircular arc of radius r. Step 1. Find m, the maximum size of f of z on the arc. On c sub r, the magnitude of z equals r, so the magnitude of f of z, which is 1 over z squared, equals 1 over r squared. Step 2. Find L, the arc length. Since this is only the upper half of a full circle, L equals pi times r. That's half the circumference of a circle of radius r. Step 3. Apply the ML inequality. The magnitude of the integral is less than or equal to m times L, which is 1 over r squared times pi r. Multiplying these out, the r squared and one of the r's cancel, leaving pi over r. Step 4. Take the limit as r approaches infinity. As r grows without bound, pi over r shrinks towards 0. Conclusion: since the bound itself goes to 0, the integral over the arc must also vanish as r approaches infinity. This has been checked numerically too. The exact value of this integral turns out to be 2 over r for every r, which always sits comfortably under the pi over r bound, since 2 is less than pi. Direct numerical contour integration at r equals 5, 10, 50, 100, and 1000 confirms that both the exact value and the bound shrink to 0 as r grows, with no sign errors and no surprises. This is exactly the kind of argument that lets you throw away the curved piece of a semicircle contour, leaving only the straight real axis piece behind, the trick used throughout improper real integrals solved with residues.